Hello again. Thank you for joining us. This is Space Nuts. My name is Andrew Dunkley. If you've never heard of Space Nuts, where have you been for the last 10 years? Good to have you along if you're a first-timer, and everybody else who's been with us for eons. Today on the show, we will be talking about a really interesting and some might think scary development, nuclear space policies. I don't think they're talking about, weapons of mass destruction, but they are talking about power supply systems. We're also going to look at SETI from the far side of the moon, because that's the best place to listen for alien civilizations because, well, Earth is very noisy. But the far side of the moon, you can't hear a thing, except the aliens, apparently. And, oh no, the Hubble tension debate is simmering again. We'll get into all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to nuke a few stories is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Lovely to hear your voice and see your face.
Yes, my voice is still a little bit down. Like I could do an Elvis song as a backing vocalist.
Oh, you could, yeah.
Yeah, way on down.
Well, so at the end of the show, you definitely need to say, thank you very much.
Thank you very much. That's what happens when I get a cold. My voice just goes down deep. When I first started in radio, I did midnight to dawns in the days where they didn't automate it. Everything was live. And around 4 a.m, when I used to get really, really tired, my voice would just naturally go down there. And it was really weird because it wasn't my natural voice, but at the moment it's enjoying that part of the spectrum. So yes, hopefully it'll get better soon. I don't like the feeling, I must say.
No, you wouldn't.
Anyway, we battle on, don't we? No point getting all...
That's...
We
do in Space Nuts. We, come rain or shine or absence or whatever, we keep going.
We do. Speaking of battling on, nuclear energy. This is a policy that's just been announced by the Pentagon and the Department of Energy, and they've kind of dragged NASA into it. They said, hey, NASA, we want you to build us a couple of power stations, and they've got to be nuclear, and they've got to be ready by 2028. How about it?
Yeah, that's more or less it. It's a 6-page policy document. Its title is NSTM-3. Which is to direct a parallel and mutually reinforcing set of design competitions by NASA and the Defense Department to enable, and I'm quoting here, to enable near-term demonstration and use of low to mid-power space reactors in orbit and on the lunar surface, and prepare to deploy high-power reactors in the 2030s. I'm quoting here from people who are closely involved with this. For this to work, it has to be a collaboration between multiple government agencies. Well, that's a novel idea, isn't it?
Yes.
That's the way
that'll work.
Yeah, that's the way that we do the right R&D and get the right tools in place for these events to unfold over the next few years.
Yeah.
Yes. So that's right. So the bottom line is NASA is directed to start work within 30 days on a mid-power space reactor generating at least 20 kilowatts of power with a variant that can operate on the lunar surface. He calls for the agency to work with multiple companies on reactor designs, including for a low-power system that produces as little as 1 kilowatt, if doing so offers lower cost and schedule risk. And this is it's a White House release that I'm quoting from here, so it's definitely the official thing.
Yeah, wow. Should we be surprised by this, though?
No, we shouldn't. I mean, actually, we did get, was it Jared Isaacman, the new, relatively new head of NASA, who, I think we covered this quite a few months ago, talked about the idea of using a 100 kilowatts nuclear reactor on the lunar surface, because that raised a few eyebrows. But it looks as though this is the first step in in expediting that to start small, maybe even as small as 1 kilowatt. It'll run an electric fire and keep going upwards. There's an interesting disparity in the sort of urgency of this, though, because the next paragraph of the White House release says the policy calls on the Defense Department to provide a briefing to the White House in 90 days on potential uses and payloads for space nuclear systems of varying power levels. The Pentagon will, in the first year of the policy, use its space nuclear funding to support NASA's efforts, then conduct its own competition for space nuclear power systems. I get the feeling here that there's going to be too many fingers in the pie and too many people deciding which companies are going to get the contracts to do this.
The options for nuclear power these days are so much more available and simple. Like you can make very small nuclear power stations now. You can build one that's small enough just to service a town these days. You don't need these big complex setups anymore. So it probably is the logical way to go, even though when you say the word nuclear, everybody sort of runs for the hills. Not that would save them. But it's not as big and scary as people envisage, but it's got bad press for a long, long time. So whenever you talk about nuclear power station, well, look at what happened in Australia. We're so scared of it, we've never done it.
And people think of 3 Mile Island and Chernobyl. And the bottom line is that if things go wrong, you have a very big environmental problem, and that would be the case.
Look at Fukushima, with the earthquake and the and the tsunami. That's a mess.
Yes, so it is scary. I think. So I grew up in a country that pioneered nuclear power with the US, and there are several nuclear power stations. I used to live not very far from one, actually, at Torness in Scotland. Is that right? Yes, I think it's Torness. Everybody just regarded it as a normal power station. It was very much a low-key thing. And you see statistics like there's more radiation comes from the natural emissions from rocks in the UK. If you go down to Cornwall, the rocks are basically radioactive there.
Oh, wow.
There's radon in the atmosphere, but it's at a level that humans can tolerate. Humans have been tolerating it for hundreds of thousands of years, and that's...
You're exposed to radiation every time you walk outside.
Well, that's right. You are, yes. So it's got to be treated with respect. I think what freaks people out, though, as well, is the idea of sticking a nuclear reactor on top of a rocket and then sending it into space. And there was an accident So just stepping back, NASA has used their RTGs, radioisotope thermoelectric generators, I think that's what it stands for, on several spacecraft, including the 2 Voyagers. I think the Pioneers have got it as well. The Curiosity and Perseverance both have RTG power supplies. So that's a well-trodden path. But there was an accident, I think it might have been in the 80s, with a spacecraft that was launched with something like an RTG on board. And it went wrong. I can't remember the details, but I think it was Canada that took the punch, and there was a lot of radioactive debris that got spread over very, very sparsely populated regions of northern Canada.
Literal fallout.
Yes, that's right. Yes, exactly. It falls out of the sky. If I remember rightly, I'm digging up things from the past here, but I think that's the case. And that clearly freaks people out. If you've got a launch that doesn't work, what's going to happen?
I imagine so, but it certainly does ramp up the space race between the US and China. China's probably going to fall a bit behind here because I think they were trying to set up a coal-fired power station on the moon. Might slow them down a bit.
Yeah, China's doing pretty well in
they are doing
sustainability. Yeah.
Yeah, they are.
But yeah, they do use a lot of coal still. Yeah,
They do. So this is probably going to happen. And what other option would there be? That's the thing. I mean, some people will say, no, put up solar energy systems, but nuclear is probably a much more efficient way of doing it.
Yeah, well, for a start, you've got the baseline load. You're not worried about where the sun is in the sky.
Correct.
The idea of being at the south pole of the moon, which is where the focus is in terms of our exploration of the moon, it puts a different slant on it, because it means that you are looking at a very low sun altitude in the sky. The sun's coming in nearly horizontally, the sunlight. Now, that's not as bad a thing on the moon as it would be on the Earth. The Earth, as the sun gets lower, it's going through a thicker and thicker layer of atmosphere, so its power is attenuated.
Yeah.
On the moon, that doesn't happen because there ain't no atmosphere. But it does bring challenges for your solar panels. You know, you've got to build arrays that are almost vertical, and if you're looking for a big structure, then it becomes slightly different engineering issue. Plus, you've got to take all that stuff up there as well. You know, going up to the moon with arrays of solar panels in the spacecraft might not leave room for much else, whereas a nuclear reactor of the kind that people are talking about would be relatively compact.
Yes.
I mean, the RTG devices are, I think is it 13 kilograms of plutonium that they have in them, and they're about the size of a tea urn or something like that, or a drinks urn. Yeah,
it's much simpler than it was 20, 30, 40, 50 years ago.
Yeah.
And of course, they're talking not only about the moon, but people on Mars, so they'll need power as well. I know in the movie The Martian, they used solar panels, but Mars is a bit further away, so the solar panels probably wouldn't be as efficient.
Exactly.
Nuclear power makes perfect sense. Although, solar energy is quite well used in space.
Absolutely.
Artemis 2 used it.
That's correct, yes. Thinking of the different spacecraft, the one that's got perhaps the most spectacular solar panels is the Lucy spacecraft, which is on its way to the Trojan asteroids. And that's got solar panels which are huge, and that's because you're going out to the asteroid belt and beyond. Actually, you're going to the orbit of Jupiter, which is where the Trojan asteroids hang out. So you need big solar panels to collect all the energy.
Yeah, the other problem with solar panels on Mars would be dust, because it's a pretty grubby place.
Yeah, that's what probably brought an end to. So Spirit and Opportunity both had solar panels, and there were certainly times when the amount of dust was stopping the power generation, and that was cleared by Willy Willies, as they're called.
That's right.
Dust devils. That's right, on Mars. Yeah.
Fascinating. All right. So the directive has been put to NASA to start working on this, and it comes from the White House. So it's all systems go, and they hope to have something operational as soon as 2028. So they're not mucking around. In fact, I think NASA, after this was released, were given 1 month to get started. So
that's exactly right. That's the 30 days that I mentioned earlier.
No mucking around.
Get going.
Yep. You can read all about it at spacenews.com. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Well, we mentioned the moon. We'll stick with the moon. This story, though, has nothing to do with people on the moon. It's got everything to do with people that are not on Earth or the moon or Mars, for that matter. They're out there somewhere. We're looking for them. We're talking about the search for extraterrestrial intelligence. And the dark side of the moon, the far side of the moon, is the best place to start looking.
That's right. So we've been looking for this for 60 years.
Yeah,
and using ground-based antennas here on planet Earth, which are very, very capable. Once the Square Kilometre Array Observatory comes on stream towards the end of the decade, we'll have the finest, most capable radio telescope in the world, which will not directly engage with SETI programs, but it will have the sensitivity to detect, well, the thing that my colleagues tell me is it'll detect an airport radar at 50 light years.
Yeah.
So that's the kind of sensitivity that you're talking about. But the main problem with ground-based, with Earth-based radio telescopes is that they're compromised by all the cacophony of radio signals that surrounds us, from your mobile phones, from broadcasts, from people like you and me doing this, going out into the ether.
Wi-Fi routers.
Wi-Fi, the whole thing, microwave ovens, it all provides this noisy radio background. And that's not getting any better with the satellite mega constellations.
Correct.
I was in a meeting yesterday where we were, it's a meeting of the International Astronomical Union Centre for the Protection of the Dark and Quiet Sky from Satellite Interference. And it was, one of the things that's raising anxiety is the idea of Elon Musk's million satellites for orbital data centers, and this mirror in the sky idea, sunlight on demand, that also has 1 million satellites with mirrors on it. So that's more for the optical astronomers, but it's all a concern, and it basically is eroding our capability slowly but surely to detect faint extraterrestrial signals. So that brings us to currently possibly the best place to do this sort of thing from, which is the far side of the moon. And we have one spacecraft, by we I mean humankind, have one spacecraft on the far side of the moon. It is China's Chang'e 4, which soft landed on the far side of the moon back in 2019. Can you believe it? It's been there 7 years. It's quite extraordinary. But now that spacecraft was not set up specifically for looking for SETI, search for extraterrestrial intelligence, but it's got a low-frequency radio spectrometer on board that actually has been used to conduct the first ever SETI search from the lunar far side. And so the goal, the idea, is to use that equipment, which is designed to do natural sciences, but to look for those techno-signatures, techno-markers, they're sometimes called, which might suggest that you're getting a signal from an artificially generated source. And what you're really looking for are periodic bursts of radiation with perhaps regular intervals that are not easily explained by natural processes. And you've got to think back to Jocelyn Bell Burnell and her discovery of the first pulsar, because that's what she saw. Narrow band in time signatures or bursts of radiation, which we now know is the pulsar, the kind of lighthouse beam of radiation from the pulsar sweeping round and passing the Earth. She didn't know that then, so she wrote "Little Green Men" in her on her chart recorder. Very, very famous words. So that's what basically the Chang'e low frequency radio spectrometer has been looking for, and it's things that that speak of an artificially generated source. And so what they've done, the scientists working on this. Basically, they built an algorithm that trawled through the data, looking for anything that might be artificial, with no credible candidates revealed, nothing that couldn't be explained either by natural phenomena or by instrument issues. There's a nice comment, though, from phys.org, who is carrying this story. I'll quote this: "This is not a failure, it is a beginning. As Carl Sagan once put it, absence of evidence is not evidence of absence."
Brilliant.
That's a really good point.
I had a lot of time for Carl Sagan. Very wise man, and he did a lot for astronomy during his time, but it's a valid point. And I suppose you and I have spoken about it in the past. The big problem is distance. There might be civilizations out there that are advanced and capable of communication, but they're so far away we will never hear from them. Maybe.
That's right. And time is the other issue. It's a needle in a haystack, both in distance and in time, because you've got to hit your civilization just at the right time.
Yeah.
When they are technological enough to have airport radar, for example, but haven't wiped themselves out because of the loonies that they've generated.
Yeah. You're more likely to get a TikTok of some kid doing a stupid rap song. That's what you'll get from an extraterrestrial intelligence. What I wonder is, with the far side of the moon, yes, it's radio silent, but does it cover enough of the spectrum of the universe to pick up something, or is it fairly narrow in its scope?
Do you mean in terms of direction, or
being able to pick
frequencies?
Something up? Has it got like a wide array?
I mean, the far side of the moon. If you plunk something on the equator of the moon on the far side, over a month you cover the entire sky.
No,
if your equipment is broadband enough, and all the SETI stuff is, it's got a very wide range of frequencies. Although they do tend to concentrate on what we call the 21 centimetre line. This is the specific frequency that's radiated by cold hydrogen. And they do tend to concentrate on that because everybody in the universe will be aware of that 21 centimetre wavelength, because that's cold hydrogen, which is the same everywhere.
Yeah, makes sense. All right, fascinating story. Nothing yet, but that doesn't mean it'll always be nothing. So
it's not evidence of absence. That's right.
Exactly. You can read all about it, as Fred said, at the phys.org website. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and skiing was a go.
Space Nuts.
Our final story, Fred, brings us back to that old debate about the Hubble tension. Now, the Hubble tension is measured in 2 different ways, and they come up with 2 different answers, and that's troubled people for a while. Although we did a story not so long ago that suggested, hang on a minute, the differences aren't that significant, so they're probably both right if you allow for the variables. But this story is saying, hang on a minute, we think there's a better way.
Yes, that's right. Exactly that. It's all about... So let's just backtrack. What is the Hubble tension? So the expansion rate of the universe basically is a number that was first measured by Edwin Hubble back in 1929. He got the wrong answer because he was only looking at a very small number of galaxies. But it comes about because as you look at galaxies in the wider universe, they get their velocity away from us is bigger the further away they are. And that comes about when you've got a universe that's expanding. That's the natural assumption, and we've believed that ever since.
Yeah.
Excuse me. So I've got a bit of Hubble tension in my chest there. So that's how it's normally measured. The Hubble constant, this number, which is in slightly bizarre units, it's in kilometers per second per megaparsec. Kilometers per second is the recession speed of a galaxy. A megaparsec is it 3.26? I can never remember the name. Million light years. It's the units that astronomers use for measuring distance, parsecs, and it's a million parsecs. So kilometers per second per megaparsec tells you how the velocity of a galaxy increases with distance, and that's the result of the expansion of the universe. So the Hubble constant tells you how fast the universe is expanding now. Now, the normal way of doing this is and it's actually why the Hubble telescope was created and why it got its name. We we measure the brightness. Sorry, I've got my tension back there. If you want to cut this bit out, Hugh, you're more than welcome to. It's fine now. The tension comes about. So no, let me step back again. The way it's measured is you build up a sort of distance scale ladder. So the direct measurement of star distances in outer space comes about by the parallax method. As the Earth goes around the sun, we see stars apparently changing their position with relative to very distant background stars, and that change in position you can measure, and in fact it's that gives the parsec its name. It's a parallax of 1 arc second is what it's short for, and so that's a direct geometrical way of measuring the distance to certain stars. If you can do that to stars whose intrinsic brightness you know, and these are typically Cepheid variable stars, then you can extend it because you know their brightness, their intrinsic brightness, how much light they radiate. Then you can look at how faint they are further and further on, and that's how we started off, because Hubble measured. In fact, in 1923, used these variable stars to measure the distance of the Andromeda galaxy. Once again, he got it a bit wrong by today's standards, but that was when we realized that galaxies weren't little things fruitling around in our own Milky Way. They are very distant objects. So that's the basic process. And that has now been basically elaborated by additional things which involve supernovae, the exploding stars, all sorts of other cosmic phenomena. And that's the basis of what this story is about, because that technology has now been absolutely refined to the nth degree by the scientists who are basically reporting this work. It's a study in astronomy and astrophysics, one of the leading journals, actually a European journal. And these scientists have spent a lot of time getting the answer right from this method, what we call the distance ladder or the distance scale, by invoking objects of all kinds. And so they have produced a number for the Hubble constant, which has a very, very small error. In fact, they quote it as 73.50 kilometers per second per megaparsec, plus or minus 0.81 kilometers per second per megaparsec. So they're talking about something that's either somewhere between 72.0 and 72.5 and 74.5, thereabouts, which is a very, very tight estimate of this velocity. So what's the tension about?
Until somebody debunks them.
Yeah, it's true. I do remember back in the 70s, and I've told you this before, Andrew, there were two schools of thought, both offering measurements with very tight error limits, one of which said that the number was 50, and the other which said the number was 100. Yeah. And lo and behold, when the Hubble telescope gave us the right answer, it was basically at the average of those two, around about 75. And it's now been refined.
It's kind of what they're doing with this, isn't it?
A little bit, although they're really giving tight, very tight estimates based on everything that we can observe. Right. Whereas the previous, this with the difference between 50 and 100, and that was a kind of Hubble tension. We didn't call it that, but that's sort of what it was. That was based on just individual measurements from their own particular school of thought. One was galaxies, one was supernovae or something. I can't remember how it worked. I can't remember the details. Probably could if I thought about it. But this brings them all together to get this super accurate so-called value of 73.5. So the tension is that there is another way of determining the Hubble constant, and it involves observing the cosmic microwave background radiation. That's the radiation that we see from the Big Bang. We're looking back 13.8 billion years to see that what's sometimes called the afterglow of the Big Bang. It's really still the light of the Big Bang that you can see because you're looking so far back in time.
Yeah.
And that gives us a different number. You can look at the it's what's called the power spectrum. The cosmic microwave background radiation has these tiny, tiny fluctuations, and by tiny I mean the amount, fluctuations in temperature. You can measure the temperature of the radiation. And they form in little blobs, and we think that's where the galaxies came from. The cooler parts were where galaxies formed. The warmer parts were not. And so there's the microwave background radiation. When you look at it, it looks like a wallpaper pattern, which is why I sometimes call it the cosmic wallpaper, partly because it's behind everything else, just like the wallpaper in a room is behind everything.
Yeah.
But it's also got these patterns. So you can use those patterns to make another estimate of the Hubble constant. And the answer that you get is 67 kilometers per second per megaparsec, which is well outside the error band of the sort of traditional method. And so I think what the direction this is going in is, so as you and I have spoken about before, people have done a lot of work to try and look for where we've gone wrong here, because these two numbers should give you the same answer, but they don't.
But they don't.
And so now people are turning it upside down and saying maybe the fact that they don't give the same answer is telling us something about the physics of the universe that we don't know.
Or we're just not accounting for everything we need to put into the formula.
Yeah, there's that too. But I think that's, so as time goes on, people are ticking off all those things. Simply because there's a lot more work being done on this topic. So the Hubble tension could turn out to be the gateway into new physics that might tell us about dark matter and dark energy and all the other dark stuff that we think about. Yeah. So it's potentially something that I think scientists everywhere will keep an eye on, but it is really in many ways getting quite exciting that this Hubble tension is not going away.
No, definitely not. It's come up a few times in the last 10 years that we've been doing this, so
Yes, right.
They keep looking at it, and very good reasons to do so. For the record, a megaparsec is approximately 3.26 million light years. I think that's what you said.
It is what I said, yeah.
Yes.
I could never remember. I think it's 3.26, that's all.
That's what I found, yes.
Yeah.
Very good. All right. Hopefully they've finally cracked the Hubble tension debate. I guess we'll find out if they keep coming up with different numbers in the future. But you can look it up at dailygalaxy.com, or you can read the published paper at Astronomy and Astrophysics. Fred, that brings us to the end of the program. Thank you so much.
A great pleasure, Andrew. We've covered some great topics today, and it's always a delight.
Yeah, it's very, a few different types of stories this time around, which we like. We'll catch you on the next one, Fred.
I guess we will. Yes, sounds good.
Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio. He couldn't be with us today because he caused a bit of hubby tension at home. And he's been sent to the naughty corner. Don't forget to visit us online or visit us on social media. And don't forget to send us your comments and questions via our website, spacenutspodcast.com or spacenuts.io, and leave reviews from your favourite podcasting platform in the meantime. From me, Andrew Dunkley, thanks for your company. We'll see you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.